This tutorial is going to be an introduction to the last chapter in our thermal unit, thermodynamics. And thermodynamics using as a very broad term that it really is a hybrid between the ideal gas laws and the law of conservation of energy. It's generally associated with engineering devices such as steam engines, combustion engines, which are obviously more common today, refrigerators, air conditioners, anything that involves tapping into internal energy of a material. Okay, so I'll demonstrate a few things in class. If we didn't demonstrate already, much of this is physics we're already familiar with, but now we're going to look at it in a very specific process. The key process is going to be cycles, where we're going to try to get something out of a system and look at how much energy is involved and ultimately how much efficiency we get. So to begin, let's look at what we already know. All right, so we're interested in internal energy, U, and we want to change it. We want to tap into it because we've alluded to before, let's say in the oceans, or for that matter, the atmosphere or the earth, there's essentially unlimited amount of internal energy. And that internal energy is something that we want to use to get work out of, okay? So if we want to understand how to tap into internal energy, we got to understand the processes that allow that to change it, and we've discussed it before. That's work, and the other is heat flow. Okay, and the big picture idea, in its simplest terms, is we want to use internal energy, U, to do work via the flow of heat. So it's an interrelationship between U, W, and Q, such that we follow, you must follow, the first law of thermodynamics, which is really nothing more than conservation of energy. Okay, so the base equation for thermodynamics is a very simple one. The change in internal energy in a system, okay, that's what we're trying to tap into. We're either lowering it or hiring it or raising it. Generally, we want to lower it. We want to tap into it, take something out, and put it into something else, is going to equal, very simple, to the work done on the system plus any heat flow into the system. Okay? Notice that our terms on the right don't have a delta in front of it because they're processes. They're, by definition, they're creating change, and our state equation or value here is internal energy, which is a particular value. Now, a few reminders. Delta U in of itself can be calculated for a gas at least as 3/2 NR delta T. So a very important association with delta U is that delta U always goes along with the change in temperature. That's a very, very important association or correlation. You change the temperature of a system, there's automatically a change in internal energy. It doesn't necessarily mean there's heat flow in or out or even work on, because there's two different ways we can change internal energy. Secondly, we want to be able to calculate the work done on a gas independent of the first law of thermodynamics. So the equation for that, we derived that earlier, and I'll do it again very briefly, is negative P delta V. Okay, now delta V is very important. You need to have a change in volume. And you don't need to write this derivation, but I'm going to put it down anyway just so you can visualize this. Work, by definition, is a force times distance. And if we're talking about a gas, we can convert force, or we can call that pressure times area. Pressure times area times distance, that distance is a volume. So that's really just PV. Okay, so we saw before that PV has units of joules. But if we're talking about work, you need motion. You need something to move. So you need a delta V there. You got to have a changing volume, because a pressure without any change in or any motion in the gas with it, which of course by the volume, isn't work at all. Okay, the reason for a negative, I'll talk about in a second, but that's just to keep things consistent with expansions and contractions. All right, so let's talk about work, W, because there's a lot of detail in the W term. Notice in the equation I wrote W on. Okay, and there's two ways you can look at work done in a system. You can talk about work done on a gas, or you can talk about work done by a gas. And you can even talk about work done on a piston or work done by a piston. So a simple model that we might want to look at is, let's say I have a cylinder. In this cylinder I have a piston. Okay, here's my piston, and then I have gas. And I can expand that piston, I can contract that piston, and I can talk about one of four things. I can talk about work done on the gas by the piston, work done on the piston by the gas, work done by the gas on the piston, or work done by the gas on the piston. Oh, I can't remember what I just said there. So we want to make sure we understand the difference there and what the correct signage is. One negative, one is positive, because it's not something you normally think of, but it's critical to get the things to balance out. Okay, so let's start with what the equation has. The equation implicit is positive work done on. So that's work done by a piston to compress a gas. Okay, so the subscripts here, the on or the by default refer to what's happening to the gas. And that things don't just happen to gas in and of itself. There's got to be some object that does the work done by, and then we have the on. Okay, so work done by a piston on a gas to compress it. That's positive work. Now let's see why that works out from our equation here. Well, delta V is by definition final minus initial. So if I compress a gas, this is going to be negative. So if I take a negative of a negative, I get a positive work done on. Okay, so that's, go through that a few times before you get there. Make sure you get that clear, because that's going to become important. Okay, negative work done on a gas is equivalent to work done on a piston. Oh, excuse me, my bad. This is a little bit awkward, but it'll work out. Work done by a piston to expand a gas. Okay, and actually I don't like the way that's worded, so I'm going to change that. My apologies. I'm going to do this on the fly. We're going to say work done on a position when the gas expands. So I'm not going to change that. When expanding the gas. Okay. So in other words, if we take our piston up here and the gas is expanding, okay, we're doing work on the piston, work done by the gas, and so we're going to get a positive change in volume. A positive change in volume when multiplied by a negative value gives us negative work on. Okay. Another way of looking at this is positive work done on a gas is the same as negative work done by the gas. And negative work done on a gas is more easily understood as positive work done by a gas. This is generally a compression, and this is usually an expansion. Okay, so I know it may sound very confusing, and I probably haven't helped by changing the words here, but look this over and come in with any questions. So let's take an example, the heat engine. Let's try to apply this concept. All right, so the goal again of a heat engine is to extract energy from internal energy and get work output. Okay, so let's take something that might have a lot of internal energy, hot water. Okay, lots of internal energy, but not ideal. Why? Because it's hard to get it to do work. In other words, remember, to do work you need to change the volume, and liquids really aren't compressible, so you can't change their volume very easily. So one way around that is to change it into a gas. And what happens when you change it to gas, you get a high temperature and you get a high pressure. And then you can have the gas, i.e. the steam, do work on a piston. Okay, so you take the internal energy you get from creating a gas, which at high pressure, and you can apply that high pressure to a piston, and you will get it to expand. Okay, so the work done on the piston will be simply, since we're expanding it, negative P delta V. All right, we'll leave it like that. I can take that back. It'll be, since it's work done on the piston, which is the same as work done by the gas, that'll be negative work on gas, which is positive P delta V. It doesn't really matter. So even I get confused by this. So let me write that again. So that's positive P delta V. All right, we call that the power stroke in an engine, but you don't need another term. So we've expanded the piston, and then that piston can be connected to a drivetrain, or it can lift something up, and that's what we call the power stroke. However, we want to continue this, do this again and again and again. So in order to repeat this, we must first compress the gas. Okay? And so if we compress the gas and we calculate the double W on the piston, since it's going to be decreasing in volume, we're going to get negative P delta V. All right, it would make sense that the work done on the piston in the downstroke or the return stroke is going to be the opposite as the power stroke. So if we do the net work for the whole two-part cycle, we see that W net is the sum of these two, which is 0. And that's really problematic. So this is telling us that it's not easy to get net work out in this simply using of a hot temperature object to expand it. Because if you compress the object at that same temperature and therefore the same pressure, you're going to have the negative work done on the object that you want, and that's going to cancel out any positive work you did. So we need to get around this. This is huge. It's a subtle point. So look it over and make sure you understand what I'm referring to here. So how do we get around this? Well, the solution is, to be of any use, you must decrease the pressure during the compression cycle so that the net work is greater than 0. So in other words, we expand the gas at high pressure and then we compress it at low pressure so that the P part in the work done in the return stroke is lower than before, so the net value is something other than 0. Okay, that sounds good. We can do that. So how do we do that? We reduce the temperature using the gas laws of the steam as it does work. Okay, so when I compress it, I got to reduce the temperature in order to reduce the pressure by the gas laws. So that requires a low temperature reservoir. Well, actually, I might use reservoir. A sink is actually the better term. And this brings about a whole different set of problems, which we'll talk about. So let me show you, let's talk about this nice little schematic right here. This is a schematic of a heat engine, and you want to understand what it's telling us, okay, in terms of energy flow. That's basically what it's about. We take a source of high temperature, high internal energy, and we get heat to flow out of it. Well, in order for heat to flow out of it, process, you got to have it flow from high to low. Okay, and in the process, through some cleverness, we can get some work to get out of it. All right, so if we put it all together, so we've got to go from high to low. That's the only way you can get heat to transfer internal energy. You can do some work. So the flow is basically QH, right? That's our input, equals W. Okay, I'm not going to put any subscripts here, so that's not important right now. That's what we want, but there's got to be some heat output to the sink, right? The colder part. And this has an important implication. So I'm not sure what I'm trying to say here, so I'm going to skip this. Okay, so if we want to look at the efficiency of this, right, how much we get out versus how much we put in, it's pretty straightforward. Efficiency E would be equal to what I get out. What I'm interested in is the work. I'm not interested in the energy that goes there. That's just waste, if you will, unless you can recycle it, divided by what I put in, and what we put in is QH. Okay, so look at that for a second. Make sure you understand why our efficiency is what we get out versus what we put in. Now, according to this equation up here, W would be equal to QH minus QL all over QH. And this term tells us something fairly depressing. And this goes to the heart of trying to extract useful work out of the internal energy of a source. You must rely on heat flow. In order to rely on heat flow, you must have something hot, your source, in contact with something cold. And so the colder part's going to get warmer. So if you look at this term here, you notice that the numerator is always going to be less than your denominator. In other words, our efficiency must always be less than 100%. There is no process that you could do in terms of a heat engine where you get 100% efficiency. No matter how good your machines are in terms of friction and whatnot, this is inherently going to be a less than 100% efficient. And we're going to find out it gets worse than that. Okay, so a lot of this is very abstract, even though the math is pretty straightforward. So review the key points again and come up with questions, because our next step is to follow a cycle numerically, looking at pressure, volume, and temperature to do these Q and U and W calculations to find out how much efficiency we get.